You guys, welcome to week 2 of honors chemistry. I hope you guys did well with week 1 and that went smoothly. So let's go ahead and move on to week 2. Now, in week 2, what we're going to be doing is we're going to be looking at a topic called stoichiometry. Now, this can be sometimes a challenging topic because it does require some math, and we're kind of combining some of our balancing reactions and implementing a math idea. So with that being said, I want to make sure that you guys reach out with questions and that you guys come to my office hours and ask questions so I can be solving problems with you guys and helping you guys along the way. So what I want to talk a little bit about is this idea that a balanced reaction is actually a lot like a recipe. So what I have right here is I actually have a recipe for banana bread. So we have a couple different things when we look at this recipe. The first thing that we have is the amount, and the amount is by that I mean we have a number, we have how many. Then we have a measurement, and we have a measurement that refers to that amount. So for example, if you look at the first thing, we have 2 cups. So the 2 represents the amount, the cups represents the measurement. And the last thing that we have is the substance that they're talking about. So in this case, we have 2 cups of flour. So it doesn't refer to anything else. And then we have, for example, 1 teaspoon of baking soda. So we have 1, which is our amount, teaspoon, which is the measurement that is being measured in, and then baking soda, which is the product that we're measuring. So if we think about this recipe and if we were to put all these things together, what we would see is that we would be able to produce 1 loaf of banana bread. Now, when you look at this recipe, there are a bunch of ratios that you guys are seeing that you guys might not have recognized. And what I mean by that is that all of these different ingredients have to be in specific ratios, and they're the same ratios that you see within the recipe. And you can't change those ratios. If you change those ratios, you'll actually be changing the recipe, and you might not get the exact same banana bread that you got before. So, for example, if we were to look at the ratio of flour to butter, what we see is that it is a 2 to 1/2 cup ratio. We may get that from our recipe. For every 2 cups of flour, you need 1/2 a cup of butter. If we were to double the recipe, we would need to double both of those. We can't double one and not double the other. If we were to look at another example, for example, eggs to ripe bananas, it is a 2 to 2.5 ratio. So again, if we were to double the recipe, we need to be doubling both of those. We would need 4 eggs and a total of 5 ripe bananas. So important ratios. So how does this relate to our balanced reactions? Let's go ahead and look at a balanced reaction. So here's my balanced reaction. And there's a couple different things. So let's kind of write this out with our amount, our measurement, and then our substance. So the first thing that we have is we have 2 moles of magnesium. Now remember last week I talked about this idea that we could read a reaction with measurements, and I said that we can use moles or molecules. We can't use atoms in this wording. So we have 2 moles of magnesium. Now when we're doing stoichiometry, we always talk about moles. We don't talk about molecules. So we'll keep with the moles. And for the next thing, we have 1 mole of oxygen. So those 2 things react and we will produce 2 moles of magnesium oxide. So again, notice a lot like a recipe. We have the amount, we have the measurement, which is moles, and we have the substance that we're talking about. Now, magnesium will always react with oxygen in a 2 to 1 ratio. And again, we get that ratio from the coefficients that we see in a balanced chemical reaction. If we were to talk about being produced, magnesium will always produce magnesium oxide in a 2 to 2 ratio. Again, looking at those coefficients, we have a 2 moles of magnesium and producing 2 moles of magnesium oxide. So a 2 to 2 ratio. If we were to double the amount of our reactants, we would then double the amount of our products so that we keep that ratio the same. Now, what if we wanted to change the amount? What if we were to change how much we were reacting? So let's look at this problem. Knowing that reactions will always react in certain ratios, we can use those ratios as conversion factors to solve problems like this. So using that same reaction that we just saw on the previous slide, how many moles of magnesium will be produced if 4 moles of magnesium react completely? Now, some of you guys might be able to do this in your head because this is a very round, easy number to deal with, but let's look at what this looks like if we were to apply some math ideas to this. So we want to be able to say, if we have 4 moles of magnesium, how many moles of magnesium oxide will be produced? So we need a way of converting moles of magnesium to moles of magnesium oxide. So let's start with our moles of magnesium. We have 4 moles of magnesium. Now, if we want to convert this to moles of magnesium oxide, we need to get our ratio. We need to get our mole to mole ratio that comes from a balanced chemical reaction. So I'm going to go ahead and I'm going to implement that. I have my 2 moles of magnesium oxide over 1 mole, or excuse me, over 2 moles of magnesium. Now, notice how I set up the problem. I have it set up so that my moles of magnesium cancel out, because you don't want moles of magnesium, you want moles of magnesium oxide. So when you are able to then multiply that across, you see that you would produce 4 moles of magnesium oxide. So again, we are using that ratio from a balanced chemical reaction to be able to convert the amount of moles of one thing to moles of another. Now, what if I asked you not how many moles would be produced, but how many grams would be produced? So based off of that reaction, what if I asked you the question, how many grams of magnesium oxide would be produced if 4 moles of magnesium completely react? So a little bit different. We know how to convert to moles. We just did that, right? How about converting from moles to grams? So what if I had moles of magnesium oxide? How would I then be able to convert that into moles of magnesium, into grams of magnesium oxide? We've done this before. How do we convert moles into grams? We use our molar mass. So we're going to add now another conversion factor into our formula to be able to convert from moles into grams. So we have our 4 moles of magnesium. We are going to convert that to moles of magnesium oxide by using our mole to mole ratio. And now to convert those moles of magnesium oxide into grams of magnesium oxide, we're now going to use our molar mass of magnesium oxide. So we're going to be using that molar mass. And so I found those values using my periodic table. So remember, we can add together 1 magnesium, 1 oxygen, and we will get 40.304 grams of magnesium oxide. So multiply that out, divide by 2, since we have the 2 moles of magnesium on the bottom, and what we get is we get 161.2 grams of magnesium oxide. So if I had 4 moles of magnesium, and if I were to react that completely, I should be able to produce 161.2 grams of magnesium oxide. Now I have this graphical representation, and this will also be on Google Classroom, so don't feel like you have to write this all down, but this just kind of gives you a roadmap on how to solve some of these problems. So starting with what you want, starting with what you have to what you want. Now, if you're given grams and you want to get to grams of something else, you need to follow this roadmap. You need to first convert grams into moles, then moles to moles using your ratios. And then you're going to convert moles into grams of what you want using your molar mass. So there's kind of like a little demo right down here. So if we have X of A and that we produce Y of B plus Z of C. Now those X's represent the coefficients and A represents the substance. So what if I was given grams of A and I wanted to figure out how many grams of B would I produce? So notice right here, I first use my molar mass of A because I need to get A to moles. That's the only way you can do it. Now, if I want to go from A to B, the only way I can do that is to use my mole to mole ratio from my balanced chemical reaction. So what you see is I have now Y moles of B over X moles of A. That's my mole to mole ratio. Now, I'm not quite there yet because it doesn't want to get to grams of B. So in order to get to grams of B, I now need to use my molar mass of B. And that is how you can kind of use this roadmap. And again, this will be on Google Classroom. I will also be posting another example of, another copy of your periodic table on there as well. So we have an example that we're going to be working out on my computer whiteboard. So let's go ahead and move over to my computer whiteboard. All right, so we're going to go ahead and we're going to start solving this problem that we see on the screen. And let me rotate my screen really fast. So we have this problem. We have a reaction, and what we have is and I'm going to actually make this just a little bit larger for you guys. There you go. Okay, so we have this reaction. We have B2H6 plus O2 produces HbO2 and water. So the first thing that I want to make sure that we do is that we need to make sure that this reaction is balanced. So what I'm going to do is I am going to write out my reaction and take inventory. So we have B2H6 plus O2, and we're going to produce HbO2 plus water. So let's take inventory, because just looking at this, I don't believe it's balanced. So let's go ahead and balance this reaction. So we have B, H, and O. And if we were to balance this, what we see is that we have 2, 6, and 2. And on this side, we have 1, 3, and actually 3. Because we have, excuse me. Let me erase that. We do have 3. I'm confusing myself, you guys. Okay, so as you see, we have actually oxygen in 2 different places, and we also have hydrogen in 2 different places. So that's important to make sure that we add those together. So let's start off by balancing our, that's our boron, so our B. So if I want to balance that, I should probably double this over here. And if I double that, what happens is that I just added another hydrogen. So now I have 4 hydrogen. And I also just added some oxygen. So now instead of 3, I actually have 4. So my hydrogen, looks like I need 2 more hydrogen. And one easy way of getting 2 more is maybe doubling the amount of water. So I'm going to go ahead and put a 2 in front of there, because by doubling the amount of water, I'm adding 2 more hydrogen. So that means that I have 6. And now let's look at how many oxygen I have. So because I just changed the amount. So if I look at that, I see that I have 4 over here, 2 over here, so I have 6. And so the last thing that I need to do is I need to balance my oxygen, which luckily that's pretty easy. I just need to make sure that I put a 3 in front of here, and I get 6. So those are my amounts that I have for that. So I have 1, 3, 2, 2. All right, so let's go ahead and start solving. So the first problem says how many moles of oxygen are needed to react with 4.55 moles of B2H6. Now, I'm going to take my time when I solve these. I want to show you guys a couple different things. So let's start with A. So what I'm going to do is I have moles of B2H6, and I'm trying to get the number of moles of oxygen. So this is a straightforward mole to mole conversion factor. And when I think about that, what that means is that I need to be able to convert from moles of one thing to moles of another. And in order to convert from moles to moles, we need to use a balanced chemical reaction. And so we're going to look at our coefficients. So what it is we have 1, remember there's kind of that invisible 1, reacts with 3 moles of oxygen. So this is a 1 mole of B2H6 to a 3 moles of oxygen. So that's going to be my balanced reaction that I use. So let's go ahead and start plugging things into my formula. So start with what you're given. And what we know in this reaction is that we have 4.55 moles of B2H6. And now I'm going to plug in my ratio. So what I have right here, I'm going to plug in my ratio. So this is going to get plugged in, is that I have 1 mole of B2H6 to 3 moles of oxygen. So notice that I put that on the bottom so that those units cancel out. Now this has 3 significant figures. So what I'm going to do is I'm going to make sure that my answer also has 3 significant figures. So if I take my 4.55, what I'm going to do is I'm going to now multiply that by 4.55. So let's go ahead and do that. I'm pulling out my calculator. And I have 4.55 times 3. And that means, oh, you guys don't need that I have 13.7 moles of oxygen. So if we increase the amount of B2H6 that we have, which is diboron hexahydride, I would then need 13.7 moles of oxygen. All right, so let's go ahead and move on to the next problem B. So now the next problem says, what mass of oxygen will be needed to burn 36.1 grams of B2H6? Now, notice that I said burn. Why did I say burn? Well, the reason why I said burn is that this is a combustion reaction. We have oxygen as a reactant, so that means that this substance is burning. So I just want to make sure you guys understand that wording. So let's go ahead and kind of create a map and think about how we need to solve this problem. So we know that we have grams of B2H6, and we need to somehow get to grams, because it's asking for mass, of oxygen. So we need to get from grams of one thing to grams of another. So if I'm thinking about that, there's a couple different things I need to do. The first thing I need to do is I need to go from grams of B2H6, and I need to convert that into moles. And I'm going to use this by using my molar mass. Then I need to be able to convert this into moles of O2. And this is going to be from my balanced chemical reaction. So this is going to be my ratio. And then I'm going to convert this into grams of oxygen. And again, I'm going to be able to use this from my molar mass. So notice that what I have here is I'm going to have 3 different conversion factors that I'm going to be plugging into my reaction, or excuse me, into my equation. So now we are starting off with 36.1 grams of B2H6. So let's go ahead and start writing out that reaction. I have 36.1 grams of B2H6. Let me make that a little bit more clear. And then what I'm going to do is I'm going to plug in my molar mass. And I've actually already calculated this, and this is 27.67 grams of B2H6. And on top is going to be 1 mole of B2H6, because that is my molar mass. Units cancel out, so I have that first one in there. Now what I'm going to do is I'm going to do a mole-to-mole ratio of my B2H6 to oxygen. So it's 1 mole of B2H6 to 3 moles of oxygen. And just did that one. So one more step, and I'm going to need my molar mass of oxygen. 1 mole of O2 is 31.998 grams of oxygen. And now I got that. So multiply everything on top and divide by the bottom. And what we end up getting for that problem is, with 3 significant figures, 125 grams of oxygen. All right, let's go ahead and do the last problem. So the last problem, how many moles of water are produced if 19.2 grams of B2H6? So we are going from grams to grams again. So let's go ahead and just map this out like I did in the previous problem. So this is C. And what we have is we have grams of B2H6 diboron hexahydride, and we want to get all the way to grams of water produced. So now we're going to be doing this kind of the same starting point of the previous problem. So we need to go from grams of B2H6, and we're going to convert that into moles of B2H6. Then we can then convert that into moles of water, and then we can convert that into grams of water. Now remember, this right here, molar mass. We need our molar mass of B2H6 again. Then right here, this is going to be a ratio. This comes from our balanced chemical reaction. And then this right here is going to be, again, a molar mass. And for example, this is going to be our molar mass of water. So that is my roadmap. So I'm going to go ahead and use that roadmap to go ahead and start solving my problem. So we have 19.2 grams of B2H6. Plugging in my molar mass of this hasn't changed. And then 1 mole of B2H6. I do need to change my ratio because now we're talking about the ratio to water. So this is a 1 mole to 2 moles of water. Let's double check that. Did I say 2 moles of water? Going back to my balanced chemical reaction. Yep, 2 moles of water. And then we're going to plug in now my molar mass of water. So I know that 1 mole of water actually has a mass of 18.015 grams of water. Let me go ahead and go back and balance, or not balance, but cancel out my units. So I have my molar mass right here, I have my ratio right here, and I have my second molar mass right there. So calculating this all out, and if I want 3 significant figures, I should be able to produce, with 19.2 grams, I should be able to produce 25 grams of water. So there is that problem. When we are looking at stoichiometry problem, we could actually talk about stoichiometry as being what are called our theoreticals. So we just solved a stoichiometry problem, and what we actually got is we got what's called a theoretical yield. And that is a yield that if everything went perfectly in a lab, we would be able to produce that much of our product, okay? Now, not everything goes perfectly in a lab. Many things happen. We don't necessarily deal in ideal situations. So in the lab, what we get is we get what's called our experimental yield. And our experimental yield is usually lower than our theoretical yield because we're usually not going to be able to produce as much. So we can see how close our data is to our theoretical by calculating our percent error. And we've actually done this before, so hopefully this isn't anything too new. And we can get our percent formula, and that is equal to our experimental value minus our theoretical value divided by our theoretical. So again, if you are trying to calculate this, you can calculate your theoretical value using stoichiometry. Your experimental value comes from an experiment. So let's take that example that we looked at in the last example, and let's apply it to this one. So we're going to go ahead and switch screens again, and we're going to solve this problem. All right, so we're going to use actually the answer that we have that we got in our previous example. So I have it up on the screen. And what we were told in the problem is that our experimental value was 22.3 grams. So remember that this right here, so what we get from stoichiometry, our theoretical is our 25.0 grams. Theoretically, if everything went perfect in the experiment, we should have produced 25.0 grams of water. However, as we know, experiments don't always go as planned, and we usually will get a little bit less. And so we actually only produce 22.3 grams. So let's go ahead and plug that into our formula. So we're going to have our experimental, which is 22.3 grams of water, minus 25 grams of water, This is going to be absolute value. And we're going to divide that by 25.0 grams of water. Multiply that by 100, and we will get our percent error. Now our percent error, let's have 3 significant figures. So my percent error is 10.8%. Not a bad percentage. We lost a little bit, but all in all, that's a pretty good percentage.